go again. I am Nico. I'm a researcher at Geometry Research. And I'll tell you a bit more about what all this is. Anna, you talked about identity protocols, Web2 to Web3, and these are all the sort of applications I want to talk about today. So proving Web2 data, this Web2 to Web3 arrow that Anna had, we have great things like zkEmail, where you can prove in zero knowledge that you've received an email from a specific domain. Web proofs and TLS oracles, which are proofs that you have engaged in a TLS session with a specific server and that some content was exchanged. There's also really cool stuff in the wallet side of things, where you have all these wallets where you can log in just from your OpenID. So that could be Google, that could be any other OpenID provider. And there's a few variants of this. There's OpenPubKey, then zkLogin, that's Sui's version, and Aptos have their version called keyless. And finally, you can also prove real-world data, and this is the sort of pure zkID kind of vibe, proving passports. You have the provable photo edits that Anna mentioned, proof of GPS location or tested microphones, and these are actually zkHack projects, so that's quite cool to see all these things merging together. But the argument for today is that all these projects are actually the same zk proof under the hood. Like, they're all the same. And this is not to say it's a bad thing, it's more an observation that I think we should all make. Maybe think about how we coordinate, and hopefully this will also help you think about all these different applications or come up with new ones. So this is the plan for the talk. Part one, we're going to look at what is this common design pattern and what's sort of the ZKP that we're all doing. And then the question is, how do we move on from here? Like, what else can we do? And then if we have time, I have a fun little technical thing that we can look at, OSNARKs. It's a bit in the weeds, but hopefully some people here will understand what this is about. Before we start, a bit of technical background. The two main things we're going to be working with are digital signatures and NIZICs, non-interactive zero-knowledge proofs. So a digital signature, you're in a setting where there's a secret key and a public key. The signer has the secret key and is going to generate signatures. And the verifier can verify these signatures given a message and the public key. The properties you get from this are unforgeability, which means if I don't have the secret key, I cannot produce a signature. And non-repudiation, which means if I see a signed message in the wild, it must have come from the signer, or their key has leaked, right? But let's say the key didn't leak, it must have come from the signer. On the other side, we have non-interactive zero-knowledge proofs. So this is non-interactive, so you have a prover verifier. The prover will send a proof to the verifier, and the verifier can just verify it. And the properties Anna mentioned earlier, completeness, sound is zero knowledge. Completeness is prover always convinces something that is true. Soundness is verifier does not accept something false. And zero knowledge means no data leak. This is a third one we need to talk about, and that we talk about a little less in these spaces. It's message authentication codes, MACs. And these are sort of the symmetric key cousins to signatures. So in this case, you have a single key that is used both for signing and for verification. This gives you unforgeability. If you don't have the key, you can't produce a signature. But because there are now two parties who have the key, you don't have non-repudiation, right? We don't know if the signature came from the signer or the verifier. Cool. That's it with the technicalities. Let's talk about how we build these applications. So the setting looks something like this, and I hope this is big enough if you're at the back. But we have some authority, auth, holding a signature key, sends a message and a signature to Alice. And Alice now wants to make a claim and prove this claim. And she's going to say something along the lines of, I know a message signed by the authority such that it's a passport issued by the British government. I have this as being verified by a blockchain, but it doesn't need to be. It's just quite useful that we have these non-interactive proofs that can be sent and publicly verified by a blockchain. What does the proof do? What does it look like? We like to build our proofs from circuits where we express the computation. And the circuit looks something like this. We're going to take in some original documents, a signature, and the public key, important. We might have some optional outputs, and we're going to do some processing. The first part is verifying the signature. And there's a few components that go into this. We're going to need some hash functions. We might need to do some math on weird numbers. We might need elliptic curves. And the second part is we need to look at the plain text and match it to some criteria. So if you're doing identity, maybe prove that someone is over 18. So you're going to have to do some string matching on the passport and a bit of math. Again, if you're doing identity, you might need to compare the image that's in the passport with the image of a person in front of you. How do we do that? I'm not sure. This is where zkML type of applications have an interesting argument. Or in the photo edits example that Anna gave, you could have here the idea that we only did the allowed edits. And that's it. That's the circuit we're all building. For zk login, for example, you're going to say, hey, I have the signature from Google saying I signed in with the username alice@gmail.com. Great. Simple. So performance requirements for this thing. Why is it that it took us so long to get here? For this to be private, we need the clients to run the proofs themselves. Or we need them to delegate in a privacy-preserving way. The latter, I'm not sure people have been focusing on too much. We have a lot of delegation, but non-privacy preserving. And so right now for identity stuff, we're trying to do it client-side. And this is where our focus are right now. Our efforts are focused right now. And these are a bunch of tweets from Zach from Aztec, all within 5 days of each other, saying, hey, I'm doing zkRSA, or I'm doing string matching, or I'm doing big integers, or I'm doing twisted Edwards curves. I wonder what Zach is up to, right? And this is not the only thing. We also have in academia this really cool paper, Reef, about using things like Nova and IVC specifically for regular expression matching. zkEmail have a very cool Python to circuit compiler where you say hey, this is the regex I want, and it's going to give you a circom circuit that corresponds to it. Or Aptos have even designed these interactive polynomial protocols for string matching that they then make non-interactive and verify within the snark in the matching criteria part. So this is not easy, and right now it's still quite slow to run client-side. We're still in the loading bar rather than spinner realm, to use Georgios's analogy. But there's hope that this is going to go faster, especially because we're all building the same thing. So it could be cool to all group our efforts here. A little variant on this topic. I did mention these TLS oracles fall in the same category. The problem is TLS uses symmetric cryptography, if you remember the max from earlier. So the setting now looks like this. Alice and the server have the session key, and now if she's trying to convince us of something, she's going to say, hey, I know a message authenticated by the server or me. And that's not okay. We can't trust Alice. So we need to prevent the prover from authenticating arbitrary messages. So we need to take the key away from her. So the first option is to use MPC. And if you squint a bit, this is sort of the same thing as before. We still have the server and Alice and a verifier. But now the verifier has to work actively with Alice in this sort of MPC setting. And here we have these key shares to represent this idea that Alice no longer has the session key. The other option is to have a proxy. So again, if you squint a bit, this is the same setting as before. But now our verifier also has to act as a proxy in the session between the server and Alice. This has only been proven secure very recently, but still under the assumption that the verifier has a secure link to the server. If Alice can sort of insert herself here, you're toast. She can put in whatever message she wants. So these are two options to sort of recreate non-repudiation, even though you don't have it. The problem is, you won't know. No, the downside is you're now in this sort of designated verifier setting. There's only one person who knows for sure that they were part of the MPC, or one person who knows for sure that they were actually acting as a proxy, and it's the verifier. A lot of the projects you see today will call them a notary, and they'll sort of ask you to trust this notary. But don't be fooled. This is a designated verifier, and the only person who knows for sure is this verifier. Cool. So what's next? What else can we build? We have this circuit. We can decline it in many ways. Wallets, identity. What else can we do? So the first thing is to generate credentials. And More concretely, this allows to avoid duplicated work. And I'll tell you why in a second. So in the real world, if I'm going to do a proof of my passport saying like, hey, I'm over 18, you want to make sure that no one can reuse my proof. Maybe my younger brother who's 16 is like, ha, I'm going to steal his proof and use it. So you need to prevent these replay attacks. But if you do that, it means that I'm going to have to make my proof every single time I need to authenticate somewhere. And if you recall the circuit, I had to verify the signature and match some criteria. The criteria might change depending on what I'm trying to prove. But if I'm still proving stuff about my passport, the signature is always the same. So when I'm doing multiple proofs of the same circuit, I am doing a lot of redundant work. And it's quite heavy. Like the signature verification is very expensive. So the idea comes from this paper, zkID, and this is a little diagram from the paper, is to have a smart contract verify this initial proof, this circuit. And if it passes, it's going to put the proof in a Merkle tree. And the root of that tree lives on chain. So that's figure 1 up there. Then figure 2, I can go to any verifier who's online and say, hey, my credential lives in that tree. And it's only been added to a tree because you know the smart contract verified my proof of a signature. And here is a proof that I matched the criteria. So you sort of split this into ways, in 2 parts. And in a way, you're caching the verification of the signature. Cool. What else can we do? Well, we can build wider systems. Once you have identity, you can do much cool things. But why is this important? All right, let's consider an example where we're building a social network that is private. So profiles are private and the social graph is hidden. Cool. What happens when I sign up? Like I see nothing. I can't find my friends. I don't want to broadcast my new identity on this network because I lose all privacy. And so you end up sort of in this unfortunate construction. So what can we do? And this is something we've tackled in a recent paper to be published at CCS, is how can we do contact matching, contact discovery in a privacy-preserving way? And to do this, we needed identity-based cryptography. And in identity-based cryptography, you need to sort of bootstrap this identity system. You need to know some kind of ground truth. How do I know that Anna owns the identity Anna R. Rose on Twitter, right? And so, of course, you've guessed it. This is where all these zkID systems come into play. You can use any of these systems, and again, any of these systems means just that one circuit, to bootstrap this kind of system. How are we doing on time? Cool. All right, 5 minutes. I'm going to cycle through this stuff really quickly. Hopefully, 10? Beautiful. Then we're going to take all our time, and I'm going to bore you with all this technicality. So, if you've noticed, so far we've been doing the zero-knowledge proof that I know a signature emitted by someone else. So the secret key exists, but I don't know it, and I'm still proving something about the signature. So I am proving in the presence of an oracle, of some third party that knows something that I don't, and that is giving me information. So what's the security in this case? So let's start with a standard security of a proof of knowledge. Prover verifier, as before, sending the proof. X is like the statement that we're dealing with. We'll call it the instance. And W is the witness. It's like the secret information that only the prover knows. And the question is, does the prover know it? This is where I have a W question mark. And usually we define this property by saying, okay, if I can have this machine called an extractor that runs on the prover and the proof and outputs the witness, then it must be the case that the prover knew the witness. Cool, that's our definition. Now what happens when I have an oracle? So you can imagine this oracle being our signer. Again, if I put the extractor around my prover and the proof, and I output W, do I know for sure that the prover knew W? Maybe not. Maybe the prover is just forwarding my questions to the oracle is answering with messages from a zero-knowledge protocol. The prover learns nothing, but is just forwarding proof messages. So this setting justifies the notion of O-snarks. These are snarks that are secure in the presence of an oracle. And because we can say like any oracle, we're going to focus on specific families. So in the case before, it was a signing oracle. And we can be even more specific. We can say a Schnorr signature oracle, like signing oracle. And so that was an example. Another example, when you have a zero-knowledge snark, you have this notion of a simulator that pumps out like fake proofs, fake accepting proofs. And so when our snark is both zero-knowledge and knowledge sound, we need this property that it still is knowledge sound in presence of the simulator. And this is sort of the same setting. It's a very special case that we prove very often, and we call this simulation extractability. But we're, in this case, interested in the presence of a signing oracle. Cool. And this is the paper introducing it from 2016. This is before sort of the interactive oracle proofs paper, or like sort of similar times. So this notion has been around for a while, but for some reason we kind of forgot about it, and we've been proving knowledge of signatures very happily without thinking too much. So bad news about OSNARKs. They do not exist in the standard model for all oracles. Like, they prove in the paper actually that you can always come up with a weird twisted signature scheme that is going to make any snark break. However, some oracles can be shown to be benign. Like, again, they don't exist for all oracles just because they came up with this very pathological signing oracle. It doesn't mean that it's always broken. Okay. There's a great article by Ariel Gabison on why Schnorr signatures aren't a problem. And this is specifically relevant to things like Zcash. At the time, that's why he wrote it, to say like, hey, even though I'm proving knowledge of things about signatures, I actually have a knowledge of the signature. Wow, okay. So in the random oracle model, which most of the snarks we use today come from, snarks, there are OSNARKs for all oracles. And most of your favorite, like IOP compiled with Fry or compiled with Breakdown, is an OSNARK. If you move to like algebraic group model or generic group model, the sort of stuff we use for KZG-based snarks, you also need to be careful about what oracles you're dealing with, especially if the oracle like messes with the group. So if you're doing KZG over BN254 or whatever pairing-friendly curve you like, and you're verifying RSA signatures, you're probably safe. But if you're verifying signatures over the same group, maybe something messes up. And finally, if you're working with something like Groth16, where you have these knowledge assumptions, I think the best we can do is just reformulate the knowledge assumption in the presence of an oracle. And this is its own assumption, like it lives in its own realm. And this is what Plumo did, like the light client for Cello. Their paper essentially does this. Cool. Summer, why? I'm not sure what happened here. So yeah, we're all building the same circuit. We verify signature and we match criteria. Maybe it's time to join our efforts or have a nice SDK that application developers can use. What else can we do? Well, for me on my wish list, the next thing is caching these credentials. And then we can start being creative about bootstrapping wider systems. And finally, just for fun, OSNARKs. Thank you very much.